warn you, today's stuff is going to look kind of hard, but it's actually not a hard lesson today. It's actually a pretty easy one. It's basic differential equations. We're going to look at two things here. We got two objectives. One is to use an initial condition to find the particular solutions for a differential equation. And the second thing is to use something called a slope field to approximate solutions of differential equations. And I'll try to explain both of these things to you in great detail. There's a lot of slides on this presentation. Please, I'm just trying to be thorough, okay? Chapter 5 is all on the differential equations. That's what we're going to spend the next few weeks. All right. The mathematics model often takes the form of a differential equation. That is, an equation that contains an unknown function and its derivative. That's why we call it a differential equation. This is not surprising because in the real-world problem, we often notice that change occurs and we want to predict future behavior on the basis of how current things change. Let's begin by looking at a few examples of some differential equations that are modeled by a physical phenomenon. One such model would be the growth of a population, which is based on the assumption that a population grows at a rate proportional to the size of the population. In other words, the bigger the population is, the quicker it can grow. This is a reasonable assumption for a population of bacteria or animals under certain ideal conditions, and I'll underline the word unlimited here. So let's identify the name and the variables for this model. We're going to let t equal time, and then we're going to let p represent the population of that particular, let's just say bacteria. So the rate of growth of a population is the derivative dp dt. So this is the derivative of the population curve with respect to time. So our assumption is that the rate of growth of this population is proportional to the population size. So that gives us k times p. Now I'm reviewing stuff from Algebra 2 / pre-calculus, proportional relationships, where k is the constant of proportionality. This equation here first models the population growth, and it's a differential equation because it is an unknown function p and its derivative. So let's go ahead and solve this. And I'm just telling you right now, I am foreshadowing to next week. Next week when we do section 5.2, which is on growth and decay problems, I hope when I say growth and decay, there's a little deja vu again. Because last year, or even maybe in Algebra 2, I hope that your teacher mentioned a formula that looks something like this. Now, if you're sitting there looking at that and you're thinking, I don't know what he's talking about, that's okay. But hopefully they've talked about these equations. Now, last year, if you had this presented to you in your pre-calc class, your teacher would have just said, hey, use this equation to solve the problem. This year, I'm going to show you where that equation comes from. And the truth of the matter is this. This right here is a differential equation, correct? Guess what the solution is for that differential equation? This right here. That's the solution for that differential equation. In fact, it's the general solution to that differential equation. Now, what's interesting about this particular solution to this differential equation, you guys probably remember it looking more like this, is when k, that's this guy right here, when k is positive, that means the population is growing. It's increasing. The number of bacteria is increasing. If that k value is negative, guess what happens then? It starts decreasing. And it actually starts decreasing very rapidly. These are exponential functions. So let me go ahead and make a point back to the warm-up. Remember the warm-up when I did the very first thing, and I can't remember what the equation is. I think it was something like y equals, I think it was x to the third plus 2x squared. Was it minus 5x or plus 5x? Minus 5x, and then plus c. Remember we talked about that curve? And I said that was the general solution because it had infinitely many curves. This is the general solution for that differential equation on the last slide. Guess how many curves we can graph depending on what C is and what K is? Infinitely many. That's the general solution. There's another model called the logistics differential equation, which I don't know that we will get to this year. That's actually section 5.4. I think we may have to skip that section. I don't know if you guys remember something from your biology class, maybe. Have you guys ever heard of something called the carry capacity? Hopefully that sounds familiar. That basically says that, like, for example, the Earth. There's roughly 7 billion people here on Earth. My question is, can there be, I don't know, can we have 5 trillion people on Earth? By the way, I don't know the answer to that question. Let's pretend that that answer is yes. Okay, fine. Can we have 50 trillion people on Earth? Maybe that answer is no. Now, maybe, and probably it's less than the trillion number. You guys would all agree that the Earth can only support so many humans, correct? At some point, we're going to either run out of air, run out of drinking water, or run out of food, right? The number of people on the Earth can't just keep growing forever. This thing is called the carrying capacity. So the curves that we saw on this last slide, this curve goes to where when x gets large or t gets large? What goes to infinity? Or in this case here, it goes down to negative infinity. In reality, most populations are restricted by some, in this case, what we'll call carrying capacity. This is called our equilibrium solutions. So they can approach some limiting amount. In fact, if there's more, let's say, bacteria than the carrying capacity, it actually has to come down to this. This model is one that you've probably not seen, or maybe you've heard about it in one of your science classes. But this is a little bit more advanced, but actually probably more realistic representation of how, for example, bacteria can grow. Okay, so in general, a differential equation is an equation that contains an unknown function and one or more of its derivatives. The order of those, the differential equation is simply the highest order derivative. So if we went back a few slides when I had that dp dt, which is the same thing as p prime, that would be what we would call a first order differential equation, because what's the highest degree of the derivatives? It's its first derivative. Okay? We could have 1, we could have 2, we could even have higher order derivatives than that. Let's look at another example of a differential equation. Here is a differential equation. You'll notice that it has a derivative, and it has an equal sign, and then it has some variables x and y on the right-hand side. It is understood that y is an unknown function of x. A function f is called the solution of a differential equation if the equation satisfied when y equals f of x and its derivatives are substituted into the equation. In other words, f prime of x has to equal x times f of x. Now guys, this slide here, actually, this right here is our first objective. In fact, it's going to be my first 2 examples that we do. If you were asked to solve a differential equation, we are expected to find all the possible solutions for the equation. By the way, this would be, for example, all of the solutions, because C could be any real number. C could be any real number. It's an arbitrary constant. That's why there's not just one equation that solves the differential equation. There's infinitely many. By the way, here's the differential equation we're talking about. So in case you're like, what the heck's going on here? We're really not doing anything different than we've been doing. It's just now we're going to kind of start applying this to real life problems. Not so much today, but we will next time. So here's my first example. Probably for objective number 1, this is the most important example. So we've got our differential equation up here, and you might think, wait a minute, Mr. Allen, this has got a degree 2 differential equation, which it does. I'll be honest with you, most of the ones you are doing in this class, you will only do degree 1 if I ask you to solve them. But this question does not ask you to solve this differential equation. This question says, determine if These things are solutions for that differential equation. So are they solutions for the differential equation? Well, let's see if we can find out if they are. And the way we're going to do that is, again, going back to this slide I talked about right here. A function f is called the solution of the differential equation if, through substitution into the equation, it satisfies the differential equation. So what I'm saying is this. This is y. Y is cosine of x. Y prime would be negative sine of x. Y double prime would be negative cosine of x. Now you might be thinking, Mr. Allen, what are you doing here? Well, here's what I'm doing. This differential equation has two things. It's got three. I mean, it's got zero, but zero is zero. It's got y double prime and it's got y. So what I'm going to do now, and this is the key idea. In fact, you know what, before I do this, let's go back to Algebra 1. You guys mind? Let's do Algebra 1 here for just a second. Let's say I gave you the equation, not the differential equation, just the basic equation, 2x plus 1 equals 7. Now, you guys probably all know that the answer to that is x equals 3, right? You guys can just do that in your head. You don't even have to show any work. You're like, Mr. Allen, that's so easy. I could have done that, no problem. So here's my question. Here's our answer. Hopefully your teacher did this. Did your teacher ever teach you how to check your answer of an equation? How do you check it? Well, you substitute it back into the equation. So let's go ahead and do a check here. So 2, and then I got to plug in 3 for the x. And then we got to check to see if that works. And you guys are going, okay, Mr. Allen, we get it. But let's just play along. We're going to do the same thing right here. We're going to get 7 equals 7. That's a check. So yes, it is a solution. Guys, I'm going to do the exact same thing for this calculus-y problem, this differential equation. Guess what I'm going to put in for y double prime? Negative cosine of x. Guess what I'm going to put in for y? The cosine of x. In other words, y double prime plus y equals 0. Well, is it true that negative cosine of x plus, let me do a different color now for that one, y, what was y? Oh, there's y. Cosine of x, is that equal to 0? Well, it doesn't take a rocket scientist to figure out that negative cosine of x plus the cosine of x is a 0, and a 0 equals 0. So is it a solution? The answer is yes. Does that make sense? Now, I want to emphasize this right now. In fact, I think you should add this to your notes. Let's do it in black. Very important note right here. I'm trying to figure out where to write it. I'm going to write it way up here. Okay, I'm going to put right here. Note, Mr. Allen did not use integration for this problem. You go back to the warm-up. In the warm-up, I didn't tell you the solution, did I? In the warm-up, I said, find the solution, basically, right? And you had to find it through integration. The point of this problem here is not for you to find the solution. Nowhere does it say find the solution for this differential equation. It says determine if these guys are solutions. Just like down here, if I would have said, hey, determine, is x equals 3 a solution for 2x plus 1? The answer was yes. That's what I want you to do. I did not integrate. Don't integrate. In fact, what's going to happen to you, and I'm just forewarning you, when you take the quiz on this, I may say check, and if you try to integrate it, I'm going to make the integral so difficult you won't be able to integrate it. And then you're going to be like, I don't understand how to do this. I'm telling you right now. don't integrate. If I give you the solution and say, is it the solution? Got it? Okay, so let's do another example. I'm going to let you do one on your own here in just a second. If I can, this still works. Okay. All right, let's look at B. By the way, what do you guys think? Is B a solution? Okay. Dagan says no. Let's find out if he's right. So, what do we got to do? We're going to do the same thing that I just did. I'm going to draw a line here. So we need to know what y double prime is. But to do y double prime, I got to first find out what y prime is. Y prime is negative e to the negative x by something called the chain rule. The chain rule says, well, the derivative of e to the negative x is e to the negative x, but then you got to take that times the derivative of negative x, which is negative 1. In other words, y prime is equal to negative e to the negative x. What's y double prime? Well, it's the derivative of this. So that's going to be, well, I'm going to do another negative, so that's going to be e to the negative x. Because you'd have a negative times another negative, which makes it positive. Now, let's see how that works in this differential equation. This is what we're trying to check here. So we'll go ahead and do that in, let's do it purple this time. So we got e to the negative x plus e to the negative x. Is that equal to 0? Well, what's e to the negative x plus e to the negative x? 2e to the negative x. Whoops, that's weird. 2e to the negative x. And by the way, guess when that's 0? Never, ever, ever. You can give me any x you want, and it will not give you 0 there. In other words, this function, if we were to graph y equals 2e to the negative x, it never touches the x-axis, ever. So this one, Dagan was right. Nope, not a solution. Make sense? Again, did I use any integration in this problem? Did not. Would you do me a favor? Would you go ahead real quickly here? I'll give you a couple of minutes. I would like you to try to determine if C is a solution or not. Is it a solution? Yeah, it's like the general solution. Anything about the problem? So what's interesting is you have that C value is a solution. But notice when we did A was a solution too. So it turns out that, by the way, it seems kind of weird that those two work. Right? But you got to keep in mind that cosine is very interesting. Just shift it over. The trick stuff, just even though I don't know, it's so interesting. It's so interesting that those curves come out, and they're both solutions. And the truth of the matter is, cosine is really just a subset of sine. They're sinusoidal curves, that's what they call it. We are halfway. What I'd like you to do here real quick is I'd like you to, I got a little poll here. I'm just curious what you guys think the answer is. For example 1, part 3, is it a solution or not? Just go ahead and answer the poll question. Guys, don't worry if you're not right, it's okay. Okay, I've had six, okay, nine people have voted, good. Please vote. Again, don't worry, I don't care if you're right or wrong on this. I'm just trying to see who's engaged. Okay, interesting. I'm going to go ahead and end the poll here if you haven't clicked anything. I'm going to end it right now. All right, so the poll, in fact, let me see if I can show this to you guys. I don't know if I'll show the results now. Can you guys see the results of the poll now? To show you? So 11 of you said yes, and 6 of you said no. Let's go ahead and see what we got here, no pun intended. First thing I'd like to point out is, do you guys know what C is? Now, C is a constant, right? In other words, it's like the number 2 or 5 or whatever. So y prime is just C times the cosine of C. Because if that had been, let's say, 2 sine x, the derivative is 2 cosine x. Because that 2 would go to the front, in front of the derivative. Y double prime would be negative C sine x. So now when we plug this into our differential equation, let's do it in blue. Again, here's our differential equation. Y double prime plus y equals 0. We get, well, let's see here. Y double prime right here was negative C sine x plus, and then y was C sine x. Does it, of course, that equals 0. It is the solution. So that one is a yes. Okay. Whoa, what happened there? Okay. Not sure what happened there. I'm not even touching anything. That just popped up. Any comments or questions on that example? Okay, again, no, I did not use integration. Not once did I use integration on this slide. Let's go ahead and look at another example here in just a second. All right, when applying differential equations, we're usually not as interested in finding the family solutions, which is what I call the general solutions, as we are finding one particular solution that satisfies some additional requirements. In many physical problems, we need to find and the words you'll hear me say are particular solutions. In fact, you heard me mention that in the warm-up. This is called an initial value problem. I will give you some initial condition like I did in the warm-up. In the warm-up earlier today, I think I said that like y of 2 was 1? Oh, yes, 0. Yeah. I think in the problem for the warm-up, I said y of 2 is 1. That's what allowed you to figure out that C was negative 5. That wasn't, so it's kind of interesting, but I've actually already tried to kind of give you some idea of how to do these differential equations before today. So we're going to look at a little bit harder example, okay? I'm just going to forewarn you, this one's a lot uglier than the last one we did. So here's what it says, there's 2 parts. Part A says verify that y equals c e to the negative x squared is a solution. And then B, it says find the particular solution. So part A is basically saying check your answer. In other words, this part A is exactly what we did on the previous slide. It's just, if you look, this differential equation is more complicated. And of course, the equation there, that's, people see those exponential functions and it kind of freaks them out a little bit. So, by the way, I would like to note that this dy over dx, that's the same thing as y prime. So in this example, dy dx, which is the same thing as y prime, we got to use the chain rule for this derivative. So that's going to be c e to the negative x squared times, and then I have to do the derivative using the chain rule of negative x squared, which I think is negative 2x. Oops. In other words, dy dx is going to be negative 2cx e to the negative x squared. Now, guys, I just ripped right through that derivative. If you were doing that derivative on your own, you might, need a couple more minutes or seconds or something to do that. Feel pretty confident, though, that that's correct. You just got to use just remember, I'm using the chain rule here, kind of going way back to chapter 2. It's just the chain rule, okay? So that's my dy dx. Now, I also got to deal with y, but the good news is what is y? Well, they already told us that. Duh, we needed that to get this derivative. So y is c e to the negative x squared. In other words, let's just go ahead and write this in black again. dy over dx equals, dy over dx plus 2xy equals 0. Is this right here, is this going to be a solution? Well, the answer is yes. We just need to show that it is. So let's go ahead and do our substitution. Here is our dy dx, so that'd be negative 2 negative 2c xe to the negative x squared. And then I got to do plus, and then 2x times, and then I got to plug in whatever c is, or whatever y is, which is ce to the negative x squared. And we need to figure out if that is indeed equal to 0. Well, I'm running out of room, so let's go over here. So that's going to give me negative 2c x e to the negative x squared. Let's go into this multiplication. Let's take this 2x times that c. So I think that would be 2c x e to the negative x squared. Okay, I mean, is it clear now? These two things are opposites. So 0 is equal to 0. Checks, and the answer is, yep, it's a solution. Does that make sense? Priscilla.
So when it references dy dx in the equation, we use the equation of y that they give us, find the derivative of that to plug that in.
Yes.
Okay.
Yes. Let me go back to let's go back to the very beginning. I've got all the work done now, okay? But we're going to go back to the very beginning. We're only focusing right now on question A. Question A is saying verify. By the way, this right here is what we would refer to as the general solution of this differential equation. Now you might say, well, how did they come up with that? We're not worrying about that today. The answer is they did integration, but we'll talk about that later, okay? They're just saying, hey, this is the solution, verify it. Okay, fine. So if I'm going to verify that this is the solution, I already know that for y, I'm going to plug in ce to the negative x squared. But what I've got to figure out is what do I plug in for this dy dx? So that's what I did right here. I had to find dy dx, which is the derivative of y. So I had to do the derivative of this, which is negative 2cx e to the negative x squared. And then all I do now is I plug all those things into the equation. And of course, I did a little bit of algebra, and it works out to be 0 equals 0. So everything's well and good. Okay, so let's go ahead now and look at part B. By the way, notice I didn't do any integration. Part B says, then find a particular solution using the initial condition. And in fact, before I do this example, I'm going to go back to this previous slide right here. This is called the initial condition, and the problem of finding the solution of a differential equation that satisfies the initial condition, this is an initial value problem. That's what we're doing here. Part B is an initial value problem. So we just established that this right here is indeed a solution. In fact, it's the general solution. The reason we know it's the general solution is because of that C right there. That's what tells us it's a general solution. Now, to find the particular solution, we just need to figure out what C is. So I'm going to write the equation again. In fact, let's do it in black. y equals CE to the negative x squared. That's the general solution. We're going to try to figure out, in fact, let me maybe write that on here too. We want to figure out what does C equal. That's what we're trying to figure out. What does C equal? Well, they tell us that the 0.02 is the initial value that we're going to use there. So that tells us y is 2 and x is 0. Y is 2 and x is 0. So all I'm going to do is I'm going to substitute 2 in for y and 0 in for x. So that's going to give me 2 equals CE to the 0. And what's what's e to the 0? What's anything to the 0? It's just 1. So C is 2. We just found C. It was 2. Thankfully, it wasn't 4, because that would have been an explosive answer. Okay, moving on. So our particular solution is y equals 2e to the negative x squared. That's our particular solution. That's here. Again, general solution, particular solution. Infinitely many curves, one curve. Infinitely many curves. All right, so that brings us to the end of objective number 1, which is to look at verifying solutions to differential equations and finding particular solutions. All right, so let's go ahead now and shift our objective here, which is slope fields. By the way, slope fields, other books and other texts and other web resources may refer to them as directional fields. They are the same thing. Okay? So suppose that we are asked to sketch the graph of the initial value problem y prime equals x plus y. And y0 is equal to 1. We don't know a formula for the solution. Now notice I'm not telling you the solution. In fact, I'd like you to think about this. Earlier today, I said that dy dx, what was that original equation I gave you? It was like x to the third or something like that?
Yeah, 3x squared.
3x squared plus
4x.
4x minus 5. I gave you this, right? And so therefore you did y equals the integral of 3x squared plus 4x minus 5 dx. Agreed? And you guys, hopefully, even if you didn't quite figure it out initially, were able to see, oh, that makes sense, I just integrate, right? Let me ask you this. How are you going to integrate that? Well, I hope you can figure out pretty quickly that the x part's not a problem, but the y part is. This tells us the variable that we're integrating with. This is not an x. That's a problem. So what I'm telling you is that you don't know the formula. You can't integrate this. And I don't mean this disrespectfully. I'm just saying you can't integrate this. You can't find the solution to this the way it's written. So someone would have to tell you what the solution is. However, there is a way that we can kind of cheat. This is the slope field for that differential equation I had on the last page. Now, what the heck? Where did that come from? I'll show you where it came from on the next example. But this slope field gives us some idea of the solution. This gives us some idea of the, let's say, graph or graphs of the solutions. By the way, there's infinitely many of them, right? In fact, look at this next slide. It's the same slope field, but now if I gave you the initial condition 0, 1, what you do is this. You put the point 0, 1 on the slope field, And then you use these marks to kind of indicate the direction in which the function should be moving. Now, I have not told you what the equation is for that particular answer, have I? But you can actually use this graph to kind of predict or approximate the solution. And I'll just let you know, in my grad program at IUPUI, one of the classes I took was called Quantitative Theory of Differential Equations. And it was a very interesting class. And for most of the problems we did, there was no way to analytically get the solution. Almost everything came down to graphing it, just like we're doing here with this slope field. Okay, a little bit more complex, but it's the same idea. What I guess I'm trying to tell you is that many differential equations can't be solved. Analytically. There's C in there somewhere and Y. In other words, you can't work it out. So we've got another choice. And there's actually another one on top of this, but I'm actually going to skip that. That's called the Euler's method, but we're not going to worry about that. I'm kind of cutting that out for right now. Let's look at an example. Now, guys, do me a favor. Don't take any notes on this one yet. Let me explain what's going on, okay? Let's say I gave you this differential equation. Hopefully you see it's got a derivative, and then on the other side it's got some function. Here's how you would try to find the slope field. In this case, by the way, does it matter what y is? It doesn't matter what y is, because whatever y is, you just take it times 0. So I'm just going to kind of leave that off. But if x was -2, if you plug -2 for x, what would the output be? It'd be -4. What if I put in -1 for x? What if I put 0 in for x? Good. Now, here's what I'm going to do. Now, I've only done 5 little examples right there. Imagine I did a whole bunch of them, and I used Desmos. In fact, if you Google search Desmos slope fields in Google, there's a Desmos program that will graph slope fields for you, and it's very handy. Now, notice this has got, I don't know, dozens of those little slopes marked. Remember, slope is just the derivative, right? So, for example, when x was 0, what was the derivative? It's 0. So look right here, guys. What do you notice about all those derivatives right there, all those slopes? They're all zeros. Do you think that's a coincidence? Nope. Guess what all these slopes are right here? Well, let's look over here. This is when x is 1, right? So guess what all those slopes are in that column? They're all slopes of 1. Can you guess what these slopes are over here? What are all those slopes? Those are all going to be 2's. Let me erase all these on this slide. What if I gave you the initial condition, -2, 4? By the way, -2 is right here, 4 is right, so we're talking about this, oops. We're talking about this point right here. So the graph has to go through that. We can use those slopes to figure out that the graph, and I kind of superimposed that, sorry, I didn't land perfectly on there. Right here is that 2, 4 down, right? So here's 4, here's -2. Here's our graph. Oh, by the way, does that curve look familiar? What curve does that look like? I hope you think it looks like x squared. And by the way, we could have done this problem without slope field, right? Look at the differential equation. The differential equation is y prime equals 2x plus 0, right? So y is equal to the integral of 2x dx. What is the integral of 2x? It's x squared plus c, right? Guess what happens when you plug -2, 4 in for that? Guess what you get for c? 0. C turns out to be 0, so this is y equals x squared. We could have done that without a slope field. In fact, you might say, Mr. Arm, why didn't you just why don't we just spend 5 minutes talking about it? Because I wanted you to see an easy example of how this works. If I had given you a different initial condition, you would have probably gotten a different curve. Okay. By the way, did we need a slope field to solve this one? The answer was no. You guys know how to integrate this. That's not a problem. So this was one where we didn't need to do a slope field. Now let's do one where you do need a slope field. Can you guys integrate x squared plus y squared minus 1? You cannot. So if I said, hey, I want you to, figure out a solution for that differential equation, you'd have to say, Mr. I can't do it. I can't integrate it. Well, even though you can't integrate it, we can create a slope field, or this is calling it a directional field. And I just use directional field here because I want you to be familiar with it either way. So here's how it would work. And this, by the way, is very tedious. I understand. Let's just pick some of these. Let's do right here. So x is this one, and y is this one. If I plug -2 in for x, so I'm plugging in -2 for x, and then I plug y in for, or 1 in for y, you would get 2, or -2 squared plus 1 squared minus 1. So that's 4 plus 1 minus 1. I think that's 4, and so that makes sense why that slope is 4. Does that make sense? Then you would do that for several different values of x and y. I'm going to pretend that we did that. And it gives us this slope field. Look at that thing. This is the slope field, or directional field, however you want to call it. This gives us some idea. So for example, if you wanted to, you could say, oh, it goes something like that, right? In fact, if we look at our next slide, here is our particular solution that we were looking for, because I said, what is that slope field going through, what did I say, the origin? Yeah, that's the origin. Let me erase this here. So the slope field allowed us to solve, if you will, approximately what dy dx equals, was it x squared plus y squared? Oh, plus minus 1. Minus 1. Going through the origin. So the good news is the slope fields are really pretty easy in terms of like I think pretty much anybody can figure out how to fill in these charts, assuming there wasn't anything too complicated. However, if you had to actually try to solve this using integration, you would not be able to do it. Oops, and I guess I need to get rid of that. Let me get rid of all this. Guys, I just remembered too. I got one more poll question here before we wrap things up. We're almost done. In fact, we are done, I think, after this. Guys, I got a poll question. I want to just talk about this box here, and then we're done. All right, so here we are. The slope field gives us some idea of the general solution for this differential equation. It gives us some idea. It doesn't give us a complete picture, but it at least gives us some idea of where things should be. This pink curve is what we would refer to as the particular solution. By the way, do we know explicitly what that equation is? We do not. We do not know explicitly what that is. It appears to be, what word would you use? What kind of equation would you say that appears to be? That's the word I would use as well. It appears to be cubic, but we don't know that for sure. It probably is cubic. Okay? All right, so that is going to bring this to an end, but before you go, I've got 2 more things for you, so please don't log out just yet. I just gave you a poll question. Hopefully you've answered that, and all you have to do is remember, I've been paying attention when I did example 3, and you'll get that answer, no problem. I've also in the chat put the exit slip that I would appreciate it if you would do. And now I'm going to wouldn't be strong as I just like to have proof that, in case I ever screw up. So I've given you the total for example 3. I've given you an exit slip. I'd like you to fill that out. The rest of this time is yours to ask me if you have questions with regard to either what we're doing today or the review that I posted last week on the Canvas page. So I'm going to mute myself, take a few minutes, complete the exit slip, and then when you're ready to ask me questions, don't be bashful. Ask away.
Can we do the exit slip?
Do you want to move forward?
I just don't know
It's up to you. Seriously, it doesn't matter. I mainly do it. Dagan, I know you're paying attention. I mainly do the exit slips because I'm trying to make sure people pay attention. I never have to worry about that with you. So let's make up for you real quick here. So let's say that I set the differential equation, let's make it really hard, is sine of x plus y over x. Let's not do that, that'd be too hard. Let's say x and y minus x cubed y squared. Now, there's no way in the world I know how to solve that. But let's say I wanted to generate a slope field for it. Yeah. What you would have to do is you have to have an x column, a y column, and then a dy dx column. And let's just plug in 0, 0 first and see what we get. So if I put 0 in here, sine of 0 is 0, right? Yep. 0. Okay, that worked out nice. So I'm telling you that slope field at 0, 0 will be like that. That's the easy one, right?
So you just have to do that
Yes.
every time for every point.
Yes. So now let's pick a harder one. Let's do pi over 4.
Okay.
And then let's pick it fairly easy. So pi over 4 is roughly a little bit less than 1, right?
Yeah.
So let's say here's 1. Let's just make this pi over 4. And then y here is going to be 1, okay? So, what was that, radical 2 over 2? Radical 2 over 2. This is radical 2 over 2. Then this is going to be 1. So that would be plus pi over 4. And then a 1. So that would be minus pi cubed over, no, get the cube that.
Oh, shoot, 64.
64. Okay, so let's go ahead and approximate what that is with her. Can you give your calculator real quick? You do square root of 2 over 2 plus pi over 4 minus pi cubed over 64. And tell me approximately what that decimal is.
Minus 5. Approximately 1.0080.
Okay, so I'm just going to go with approximately 1, which is interesting. So I'm telling you that that slope right here is 1, roughly.
Uh-huh.
And anyway, you'd have to keep playing that for different points on this, and it'll give you some. So the more points you put on it,
The more accurate.
the more accurate.
Okay, that's.
And by the way, most of them aren't that hard. Guys, just a reminder, I am still on here. If you have questions, yeah. Oh, go ahead.
For number 17, how do you find, like, huh?
Can you repeat that first part? Oh, I missed that. What did you just say, hon? I didn't hear you.
Number 17.
Okay, give me 1 second. Let me pull that up here. Okay, good. Now, it's interesting that you bring that one up now because that is actually a differential equation. So, did you do okay on A?
Yeah, I just had problems with C and E because I didn't know how you use your calculator to find the Y thingy.
So let's go ahead and make sure we're okay here. What did you get for A? What did you get for the?
I got P equals 5/4 T to the fourth power plus 1.
Hold on, go slower, okay? I gotta try to keep up with you.
Sorry.
Each of the fourth, you said, then
Plus 120 T to the 5/3 plus 800.
okay, good. I think that's what I got as well. Now, I think the question is how do I use this to find the other answers, right? Okay, so let's go ahead and get our calculator up here. And I'm gonna go, oh, good. Coincidentally, guess what I already have in here? I just have the same thing here. So that's gonna be, what is 5/4? That's 1.25, isn't it? 1.25 x to the fourth plus 120 x to the 5/3 plus 800. Now, first of all, let me make sure you guys understand how to figure out how to adjust your window. I'm going to go to zoom standard, which is 6. When I graph this the way it is, you hardly see anything in the graph. That's not very helpful. So what I recommend you do is go to the table and just look at these values. Now we're interested in mainly 1 through 10. So at 1 it's 800, or 0 it's 800, but when we get up to 10, it's already all the way up to 18,000. Okay? By the way, that's the answer for part C, I think, is it? Or part B, is it? Part B, the answer is 18,869. Anyways, so what you needed, what I did on my window is I went from -1 to, let's just say 10, and then negative 100. Well, let's do negative 1,000, and then we were already up to, what was it, 8,000? What was that?
18,000.
18,000. So let's go up to 20,000. Now watch when I hit graph. So now my grapher shows me a lot better idea of what this function looks like. So now if I want to find for part B, what is the population when t is equal to 10, I can just go to second function, calculate, value, 10, and there's the answer. So that's 18,869.907. Is it 907?
Yeah, 907.
907.
Oh.
What were we talking about here? Population. I'll just say people. Now this question didn't ask us to round, so I went out 3 decimals. If it said to round to the nearest person, then you would round that up to 18,870. Now, how about part C? How are you going to find part C? Which is, I think, one of your questions, right, Al?
Mm-hmm.
So how do we figure out when that curve hits 25,000?
So equal to 25,000.
Got it. Now I'm going to do it with my calculator though. So watch this. So when I'm at 10, I'm all the way up here to 18,000. So what I'm going to do is I'm going to make my window go out past 10, maybe go out to 15. And instead of going to 20,000, I need to go above 25,000. So I'm going to change it to 30,000. And I'm going to hit graph. Okay, that looks good. Okay, so it looks like maybe someone, well, how can we figure that out exactly? Well, what I'm going to do is in Y2, I'm just going to put 20,000. And now, remember, Y is the population. We want to know when the population is 20. So now to find my answer, one thing I got to do, and this is review from like algebra 2, right? Is just figure out where these two curves intersect. So I'm going to adjust this. I'm going to get a little bit closer to where they cross. Sorry, my calculator goes really slow because I'm using the smartboard. I'm going to hit enter, and then I like to go to a little bit to the right of where they cross. I'm going to hit enter, and then it's going to say guess. And it looks like the answer is 10.917. Does that make sense?
Yeah, thank you.
Okay, so let's look at the next question. It says, what is the average population? So let's see here. To do that, notice I circled the word average or underlined it. That means I got to do 1 over 10 minus 0 integral from 0 to 10 of our equation here. You'll notice that the dt's are going to cancel out, and you're going to get 1/10 integral from 0 to 10 of dp. And you can go ahead and figure out what that is. The other thing, well, yeah, I think that would be fine. So that's going to be 1/10 integral from 0 to 10 of 5t cubed plus 200 t to the 2/3 dt. That's what you're going to do.
We already have that, don't we?
Yeah, we did.
Okay.
Yeah. And that answer turns out to be 5388.715. Now, do you know how to do that with your calculator? Okay. And then E, when does the population equal the average one found in D? Well, we're going to play the same game I just did with this grapher, except instead of making Y2 equal 25,000, guess what I'm going to make it be? That 5,388.715. Let's see how that works. So I'm going to change this Y2 to 5388.715, and I rounded that, so I might be off from the answer I gave in the book or the problems, but let's see how this works out. Intersect. Left. Right. $6.321. Okay, good. I got the same answer. Does that make sense? I think that's a great question, and I think that students that don't take time to make sure they know to use their calculators are going to be in trouble on the exam.